most of you know that there has been quite a lot of effort up until now in the literature to basically focus on enhancing the security profile of a device, but primarily focusing on the integrity of a device. And for this, there has been also, the motivation is that there have been quite an extensive threat model, and this has always been enriched with new type of threats, new type of risks that are always been identified. And the latest trend is also in the context of trends in malware, like very advanced malware that can target the host device in order not only to disrupt its operation, but also possibly extract privacy and other sensitive related information. Now, as we are moving towards to, let's say, more automated system, more autonomous systems in the context of the entire compute continuum, which basically means that there is a service graph chain comprised of multiple heterogeneous devices and heterogeneous infrastructure elements hosting such services, there is the need to essentially enhance the concept of trust and get closer to what has been defined by the standards, that essentially the trust and trustworthiness of a system, it's not only related about its integrity, but also about its reliability, safety, dependability, resilience, and so on and so forth. There has been quite an extensive definition, let's say, although in some cases there's a bit of contradiction in the definition that is provided by different standards, but there is a convergence that basically when we're talking about trust and trustworthiness, this covers a wide gamut of properties that we need to make sure that to guarantee in order for having basically evidence on the correct behavior, on the correct operation of a device. And this is what we are basically trying to achieve. Now, when it comes to this notion and concept of trust, this comes into two flavors. So one flavor has to do basically with any type of data source, which basically is a device. So this is what we call node-centric trust. And then, of course, we also need to be able to safeguard the trustworthiness of the communications. Not, again, going beyond integrity and confidentiality, which can be done with traditional crypto, but essentially enabling and allowing the communicating parties to associate a trust level on the actual messages to be exchanged. This is what then we call data-centric trust. So combining and fusing data-centric trust with node-centric trust, it's what allows us to essentially characterize the trust level of a single device. And then based on this can be elevated to essentially then characterize the trust level of the entire service graph chain or of the entire domain where multiple service graph chains are being deployed. The common denominator, like the most important building block in order to be able to do that, is that we need to be able to have access to evidence based on which we can essentially assess the trust level of such devices. But this needs to happen in a verifiable manner. Okay, so essentially you can understand that if we don't trust the evidence based on which we are relying to assess the trust level of a device, then we cannot have, so let me rephrase, there is a lot of uncertainty, okay, on our opinion, on our characterization of the trust level of the device itself. So in order for us to be able to do this, what we need a rich set of mechanisms and protocols that are able to provide the so-called secure lifecycle management of a device. So essentially starting from the design phase, which basically allows a device to be equipped with all of the appropriate tools so that it can then later on execute all of the trust assessment protocols, trust assessment mechanisms, and establish its trust level, all the way to be able to re-establish the trust level if something goes wrong. Okay, so potentially, as an example, think of it is that we have the concept of software update, or we have the concept of being able to enforce different type of reaction mitigation strategies if essentially something goes wrong. Now, what we are doing and offering REWIRE, it's basically all of these protection mechanisms with a hardware assistance. Okay, so we're talking about basically employing root of trust, decentralized root of trust, like the very well-known TPMs. All of the computers and all of the laptops currently have such TPMs in order to be able to support operations like secure boot and so on and so forth. To trust execution environment, so there is again a wide set of different root of trust, although the core properties, the core characteristics that we are interested in is that it's root of trust for storage, root of trust for measurement, and root of trust for monitoring. So if this type of security elements, they can provide this type of properties, they can actually support and they are able to provide the capability that we are offering in REWIRE. The key takeaway message here is that essentially we need to have this type of hardware-rooted, hardware-assisted security mechanism in order to converge or convert the device into a hardware-based security token that capable to provide verifiable evidence based on which we can characterize the trust level of the untrusted part of the software of the application being instantiated inside the device. Now, in order to be able to do this when it comes to trust, there are essentially two important challenges that we need to overcome, okay? One important thing, and this is directly related with what we said about verifiable evidence, is that when you are trying to characterize the trust level of a device and you are relying on evidence, you are either relying on your own evidence or on the evidence of the devices, of the adjacent device with which you are communicating. Now, in this case, it can be the case that we are getting contradicting data, right? So I can basically say that for my neighbor, I'm seeing a behavior X, whereas another neighbor, they can actually say something different. So in the case of contradicting data, it either means that someone of the referees is basically lying, or they can actually, if something is wrong, is with the device for which we want to characterize its trust level. So all of the capabilities when it comes to trust assessment, they need to be able to cope with this type of contradicting evidence. There are quite a lot of techniques and a lot of mechanisms, usually considering probabilities and the probabilistic logic. For instance, subjective logic, fuzzy logic. This is not something that we will go into detail today, that they are able to cope with this type of contradicting evidence. And this is the assumption we make in our project, that there is existence of this type of tools and capabilities. The other important thing, it's in the concept again with the verifiable evidence, is that what type of evidence do we need to monitor during runtime that will not essentially kill the device in terms of performance overhead, but they are also rich enough to be able to allow an accurate trust assessment regarding the device. One, of course, important thing, well-established methodology there is the concept of remote attestation. So you can attest different properties of a system device based on which you can assess the trust level. But always the challenge here and the question in all of these attestation schemes is what type of properties do I need to attest, or what is the design space of those properties that if I attest them, I can actually have guarantees that my device is operating within the expected boundaries, right? Within the expected profile. Many of the existing works, they actually either assume that someone is defining these properties, or they essentially try to attest the entire software stack, which is basically impossible because the overhead that will be posed to the target device, it's so big that this will not, so it will disrupt, having the security mechanism will actually disrupt the operation of a device. And this is another, keep in mind, key requirement, converge trust with safety. So we should not be able to disrupt the normal behavior of the system by adding very, very heavy, resource-heavy security controls. And this is where in REWIRE, essentially we're one of the first, and you can see here the architecture, although I don't, and I will not go into the detailed flows, what is important thing here to hear is that we are one of the first that we are trying to basically use together, so merge the benefits of design time formal verification mechanisms with runtime trusted computing capabilities and trusted computing extensions. And what we mean by that? So there is again a lot of effort, a lot of work done in the context of different type of tools for formally verifying the correctness, either security correctness or functional correctness of protocols that will be deployed to the system configuration of a device. Now, the interesting part here is that this type of verification protocols, they can give you the design time assurances of what they can model. In many cases, we cannot model everything when it comes to a protocol, because then the model becomes so complex that it cannot converge. So it cannot basically solve it on time. So we need to make abstractions. Now, what we have showcased in REWIRE is that whatever we abstract essentially is what we need to attest during runtime, because these are the only properties for which we don't have the necessary design time assurances that they behave as expected. So we are narrowing down, we are limiting the trust sources, okay? The space of the evidence that we need to monitor during runtime, and they are enough to essentially allow us to characterize the trust level of a device. So you can actually see here, we are using a combination, what we call, it's a composition of validation and formal verification tools, different layers, from mathematical analysis of security protocols to using like Koch theorem proving, Resolute, and other type of verification tools that allow us to verify the functional correctness of a protocol. Which then, anything that we cannot verify, as we said, this is what we then proceed to the REWIRE trusted computing base, let's say. So this is what orchestrates what we are monitoring during runtime and what we are attesting, and based on which we are assessing the trust characterization. Now, the last point I want to make here, because before I give the floor to Spiros, is to introduce now the benefit of the AI-based misbehavior detection. So one concept of what we are saying, it's now use the attestation output as one evidence. And let me give you an example just to understand what we're saying. So you can basically see whether the device was executing correctly the secure boot, whether the configuration of a binary as part of the software stack of a device has not been tampered with or altered during runtime. And this can give you information that no specific threats or vulnerabilities have actually occurred in the device operation. Okay, so what about if we start providing the output of additional detection mechanisms as input to such trust assessment mechanisms? Will this allow a better accuracy in the whole mechanism, in the whole process? And you can see here an example like of a rather exhaustive list of such type of evidence that we can use as a trust source. And one of which it is actually intrusion detection systems. Why? Because they give a different perception about the system's operation. So attestation, it's mainly focusing about operational properties of the host device. Intrusion detection can also take into consideration how the application behaves. And this is where we came with Spiros in the context of REWIRE, and we basically try to use AI-based misbehavior detection systems for being able to identify any anomalies, any events out of the norm, considering now the behavior of the application, not the device. And this is given as input to the trust source. And we have 3 use cases where in 2 of which we are testing the AI-based misbehavior detection system. One, it's basically the smart satellite. So this is, I think, the one where Spiros is going to be basing its presentation, because we have already finalized a rather detailed experimentation and with some very, very interesting results. And we are in the process now to actually also doing some additional experiments in the context of smart cities, focusing on agricultural data, basically, that help. So this is in the context of, again, a lot of different data helping the management in the agricultural realm. These type of things as a second step, and this is like what we are currently doing in the project as part of the last experimentation activities, is to actually see whether such type of mechanisms can also enable more advanced attestation primitives, for instance, in the context of control attestation. So identifying violations in the execution flow of a program. There are a couple of works that showcase that this is actually possible, but they are making a lot of assumptions where we try to weaken these assumptions in our experiments. And through this, we are showcasing that the more trust sources you can have, the less uncertainty it might be the case that you actually have in your trust characterization of a system. And with this now, I want to give the floor to Spiros. We do have at the end a Q&A session for any questions that might occur. So Spiro, the floor is yours. I stop sharing my screen.
Thank you very much, everyone. Thank you, Thanassis. I hope you can hear me. Okay, so following the introduction by UBITECH, we will continue with the fundamental concepts of misbehavior detection, and specifically in embedded systems, highlighting why it matters for security, reliability, and performance, and then progress towards its practical application as carried out in the REWIRE project through the development, as Thanassis mentioned, of the AI-based misbehavior detection aging. And I will go also through 2 videos showcasing its main functionalities. So here we set the foundation by defining what is misbehavior detection, which basically involves identified unexpected or unauthorized behavior in the embedded system, which is essential, as you understand, for system reliability, safety, and security. As embedded system can be found everywhere, from your car, let's say your coffee machine, ensuring they behave correctly is essential. So now misbehavior can stem either from unintentional faults like sensor malfunction or hardware failures, or even intentional threats like cyber intrusion or firmware tampering. So it is important to differentiate between these malfunctions, which may be due to wear and tear or bugs, and security threats, which involve malicious intent. And also this distinction can also inform the type of detection and response mechanism needed to tackle this. Now, in terms of security challenges, as you understand, as we scale up IoT systems, particularly in critical domains like healthcare, smart cities, or the automotive sector, the security landscape becomes more complex. So a first security challenge faced is the massive scale of these deployments, which again introduces management challenges. We're talking about presently about thousands or even millions interconnected devices, so each of them contributing to the system complexity. As a second main challenge, we have multiple attack vectors, which are nowadays present. So every single device can act as an entry point for attackers, especially if it's poorly secure or left unmonitored. Currently, traditional security mechanisms like static firewalls or basic access control struggle to adapt to this level of heterogeneity and scale. Thus, they're often not efficient or flexible enough to handle distributed threats. So a crucial task is the timely detection of these anomalies or malfunction, which may indicate security breaches or operational failures. And this is basically where misbehavior detection comes, with the goal to identify this misbehavior before it escalates, protecting not the data itself, but also the physical processes and the system controls. This is particularly, as we understand, important in embedded systems, which are widely used in the automotive sectors, such as cars control unit, ADAS, in aerospace systems, in medical devices, such as, for example, insulin pumps or pacemakers, as well as smart city infrastructure, for example, traffic control or water system. Now, if this misbehavior goes undetected, the consequences can be serious. There can be safety risk to humans, operational disruptions, financial losses, and of course, loss of user trust. So that's why we consider that having robust, scalable misbehavior detection is not just nice to have, but it is essential. As we showed in the previous slide, misbehavior is not theoretical. It's actively protecting real-world applications in various domains, ranging from as I mentioned, from the automotive to healthcare, so safeguarding both functionality and security. Now, in this slide, we go a bit into more detail, presenting some real-world application where misbehavior detection in embedded system can play a critical role in ensuring their safety and security. For example, starting with the automotive sector, As you know, in motor vehicles, embedded systems are responsible for functions like braking, steering, even collision avoidance. So here, misbehavior detection can help identify anomalies in advanced driver assistance systems, since in this case, having some malfunction in sensor or having unusual driving behavior could compromise safety. In the healthcare industry, embedded medical devices like pacemakers must operate reliably and securely. So monitoring the system for unauthorized changes, such as tampering or firmware manipulation, is essential to protect the patient's safety and privacy. In the case of smart grids, which rely heavily on distributed embedded systems to manage power generation, distribution, and consumption, detecting anomalies again is crucial, especially in the case of power usage patterns, which can help flag technical issues or cyber intrusion, therefore support the overall grid's resilience and efficiency. Also in factories and process industries, where embedded systems are widely used to monitor and control machinery, misbehavior detection can also play a critical role, enabling early identification of equipment faults or sensor drift, or even cybersecurity incidents, which can help to minimize machinery downtime and protect the production lines. Now, in terms of common types of misbehavior, we identify four main ones. We start with the functional anomalies, which refer to unexpected behaviors in the normal operation of embedded system. These are often caused by sensor malfunctions or faulty actuators. An example in this case would be a temperature sensor constantly reporting the same value due to an internal failure. Another key type is performance degradation, which refers to systems becoming slower or less responsive over time. This can be either due to resource exhaustion or hardware aging. An example in this case is having increased latency in a real-time control system, which in turn will delay critical responses. Another key common type is the security breaches, which involve unauthorized access or manipulation of the system hardware. Includes issues like firmware tampering, malware injection, or even unauthorized configuration changes. As an example, we can say having an attacker exploiting a vulnerability in a connected device in order to gain control or to steal data. And lastly, we identified communication issues, where we refer to problems in data transmission or reception, especially in connected or network system. This can include data corruption, signal loss, or even spoofed messages that can mislead the whole system. An example in this case will be a wireless sensor receiving tapered data, leading again to incorrect actions downstream. Now, as we saw in this slide, there are various techniques that can be used to tackle the problem of misbehavior detection, ranging from traditional rule-based to more advanced machine learning, which is also the focus of REWIRE. The AI and machine learning methods can include supervised learning, which is where labeled data are used, since both normal and abnormal data are modeled in this case, with common classic algorithms that can be used, like the support vector machines, decision trees, proximity-based classifiers. We also have unsupervised learning when we don't have any prior knowledge of the data in order to predict some anomalies. This a very common method in this category is clustering, where the anomalies are identified as data points that do not belong in a specific cluster. We can also have semi-supervised learning, where the process where only normality is modeled, and any deviation within a specific threshold from that behavior is considered as anomalies. We have reinforcement learning, a method which involves foremost attention to the formulation of the problem to be used in a self-learning problem. Deep learning techniques, which use both supervised and unsupervised learning. In this method, input features are modeled within multiple layers of the network. Common techniques that can be used here include convolutional neural networks, long short-term memory and encoders, generative adversarial networks. These are some of the models we identified and widely used in the bibliography. As well as having hybrid approaches which combine rules models and the use of AI for robust detection. Now, as I have pointed at the bottom of the slide, an overall challenge that occurs in this method is the demanding computational power that's required, and this is why it is one of the main reasons where they are avoided to be used on board essentially. Now, for this part of the presentation, we can say that summarize that effective misbehavior detection significantly boosts reliability and security in embedded system. It is vital to develop strategies to mitigate these attacks and safeguard the integrity of the devices from malfunctioning. And continuous improvement of the detection method is essential to counter the evolving threats. And here is where AI-based approaches are increasingly important and used lately in order to handle the complexity and enhance the accuracy. Now, moving on going into the second part of our presentation, I will be presenting the AI-based misbehavior detection engine. It's a cloud-based solution developed and implemented in the REWIRE project with the scope to ensure the security and operational integrity of connected devices operating within the REWIRE ecosystem. Our engine employs a proactive approach to identify and mitigate threats and operates through a two-phase framework. The first one is the training phase, where we basically utilize the existing data and build the detection models. And the second phase includes the near real-time detection, where it applies the models to current data, near real-time data, in order to identify these threats. Overall, the engine is capable of detecting both external intrusion threats and internal device malfunction or unusual behavior. And this dual functionality ensures the thorough security monitoring by detecting external attacks and anomalies caused by the system failure or even operational defects within the devices. In terms of interfaces within the REWIRE framework, the engine receives the data from each analysis from the blockchain infrastructure, specifically the Thanassis secure oracle, with communicating through REST APIs. While the analysis results, which includes the engine's predictions and accompanied by confidence level, are pushed to the risk assessment module, again through REST APIs. Now here you can see basically the architecture of our engine. So starting from the bottom is basically where the input, the data, sorry about that. We have the data access data storage layer, which is responsible for ingestion of the application data from the REWIRE blockchain infrastructure and ensures sufficient data retrieval and storage. In the middle, we have the business logic layer divided into sub-layers. The backend level in blue, which handles the core analytical processing capabilities and coordinates the logical flow and the data analytics tasks. And the execution level, where the data manipulation and the analytics tasks are performed. And lastly, on top, we have the presentation layer, which serves as the user interface, allowing users, AI data scientists, to design, execute, and derive analytical insights, as well as visualize the results. Now, as core innovation points of our engine, we identify its flexible classification models. Actually, as we will see in the demos later, the engine supports integration of various classification algorithms, adaptable to different data types and domain-specific needs, and provides to the users various ready-to-use models, which, as you can see here, I have some examples of the models that are included, such as decision tree classifier, random forest classifier, etc. Another key innovation point of the engine is that it supports trustworthy AI within REWIRE, since it leverages the data veracity introduced by the REWIRE secure oracle for verifying and assessing the trust level of application data. It provides data-centric trust establishment based on security claims associated with the data, which again is verified by the town crier. and operates on trustworthy data, thus offering enhanced security in detecting anomalies. Now, as Thanassis mentioned, the engine is utilized in two use cases in the REWIRE. The first one deals with its implementation in the smart cities, smart satellites use case, where the objective is to analyze satellites' operational patterns and detect misbehavior that could compromise their integrity and operation, and flag such behavior so that a satellite operator can intervene. Overall, the AI-based misbehavior detection engine acts as a dynamic source in REWIRE, complementing attestation by capturing the network-based misbehavior, in this case from satellite telemetry, thus enabling a more detailed trust assessment. Now, for the implementation in the smart satellites use case, the data, as you can see here, include the satellite telemetries decoded from ground station, also including labeled data for various events. We used the telemetry from 11 satellites, where actually 6 were used, as this basically sorry about that. Yes, so we were provided with 11 satellites. However, only 6 of them provided fulfilled, as we can say, the behavioral. This subset efficiently showcase the complete range of behavioral characteristics. As you can see here, the attributes provided included satellites information about the name, the position, the battery capacity, as well as ground station information, name, and their position. Now, in the smart cities use case, 3 main types of anomaly were identified. We had point anomalies, where the telemetry values fall outside the operating range that we consider normal. Collective anomalies, which refer to a set of related data sequences that is abnormal with respect to the entire dataset. And contextual anomalies, where a data instance is anomalous in a specific context, but in all other situations it could be considered as normal. Now, in other categorizations of anomalies, generally speaking, that are encountered in IoT devices, can also include noise, when the variance of a subsequent data sample is increasing. Constant anomalies, that means suddenly a sensor starts to transmit a measurement of constant value despite the actual condition, as well as drift, which refers to the amount of change over time in the statistical properties of the data. Here, basically, we present the misbehavior checks undertaking the smart satellites use case. We have 3 types of checks. For the first one, we undertook unsupervised anomaly detection, basically an outlier detection, where we train and applied an elliptic envelope algorithm to detect power spike using the satellite's battery capacity as a variable. A second check that was undertaken with 2 variables. The first one is in order to identify satellite stumbling, so basically rotation of the satellite around its own axis, which is a function that can compromise the operation of the satellite. Firstly, we use quaternion telemetry data. Unit quaternions basically form a mathematical group, and it's like rotation in a 3D space. Here again, we used unsupervised anomaly detection by training and apply a CNN autoencoder on scale data to predict the tumbling using its attitude information. In this check also, we used the solar panel telemetry data, where we again train and apply a CNN autoencoder to predict tumbling using the solar panel outputs and providing confidence scores for our predictions. And a third check, which focused on identifying anomalies caused by satellites passing through the South Atlantic anomaly, which is an area of increased radiation exposure and can impact heavily the satellite operation. This check, however, is preventive. It differs from the direct misbehavior detection, serving as a proactive early warning system. In this case, we used we undertook a supervised classification, training and applying an XG booster on latitude and longitude information to predict satellites due to this South Atlantic anomaly. Now, the second use case where our engine is implemented, the analysis is ongoing, refers to the smart cities use case. In this use case, we had agroclimatic data such as soil condition, indoor-outdoor air temperature, wind speed and direction, solar panel battery levels, available all this from IoT sensors from an agricultural research center in Murcia, Spain. And this misbehavior in this use case refers to identifying significant deviation from the standard agroclimatic behavior and operational failures in the monitoring equipment, i.e. the sensors, which could indicate malfunction or even environmental threats, as well as cybersecurity attacks, which in turn could impact the smooth operation of the agricultural infrastructure. The challenges we faced in this use case included having data within normal ranges, thus there were no evident correlation to investigate. In order to tackle this, we sought expert knowledge in order for them to provide potential correlations among the data attributes, who in turn identified potential correlation between soil electric conductivity, soil humidity, and exterior humidity. And also another challenge we faced was that the data were missing labels, and again, to assist us, we undertook an early investigation and sought expert feedback in order for them to flag anomalies so we can use them as ground truth in the upcoming anomaly detection model. Now, through a preliminary analysis we undertook for this use case, and based on the expert knowledge provided so far, the potential misbehavior checks that we can investigate include unsupervised anomaly detection for detecting point anomalies, where we will continue focusing on point anomaly detection on soil humidity, utilizing the exterior air temperature and the soil humidity sensor readings as features, with potential methods to be used, including elliptic envelope and local outlier factor. We are planning to undertake as well supervised anomaly detection, where based on this expert feedback from the validation of the preliminary point anomaly results, we can use these outcomes as ground truth to train a supervised model for anomaly detection. And depending on the dataset size, we can use models such as XGBoost classifier or neural networks. And a third one, we can undertake both supervised and unsupervised anomaly detection for detecting context anomalies. Our plan is to explore the possibility of identifying anomalous events by detecting patterns in the available agricultural data within specific contexts, such as time of day or season. And to achieve this, calendar-based feature will be combined with soil humidity and temperature that can be used to train the models. Again, depending on the availability of labeled anomalies, either unsupervised approaches like isolation forest or supervised models such as XGBoost classifiers can be applied. We can also consider the utilization of neural networks, but this depends on the dataset size, if it's sufficient to support their use. Now, moving forward, I will go into showcasing the user interface of the AI-based misbehavior detection engine. Firstly, I'm gonna show you a video of a draft example how basically the engine works, and then carry on with a supervised outlier detection problem that has been already undertaken by our data scientists. So if I change my screen, hope you can still see it. So this is basically the user interface of the engine. Here on this graph view is where the users, the data scientists, can design the analytic pipeline. As you can see here where it says library, we have various, as I mentioned previously, ready-to-use blocks. We have the input blocks, we have the data preparation blocks, control blocks, machine learning blocks, and output blocks. So basically, what the user can see in the input blocks is various functions such as creating a data frame, reading a data set, or reading results already from an analytics pipeline. He can also use ready CSV files, Mongo database, read data from a Mongo database or a JSON file, or even Parquet file. So in this case, you can just basically click on this plus button and then configure the parameters for this. Here, basically, what we can do is select the intended data set and then check which of these columns from the given data sets we want to use in our analysis, in our pipeline. And also, in this case, what we can do is apply some filters. So for this example, I have from this satellite dataset, I used some filters. So basically, selecting specific satellites. So as you can see here, we can go to select a satellite name, set that the relation operator should be equal to a given name of a satellite. So basically, select this specific satellite from the whole dataset. And now moving forward, we can go to the data preparation blocks. So basically here we have basic functions that can be used. As you can see, we can append data sets, we can create new columns, decrypt some data if needed, or drop columns if there are any values missing. Moving further down, we have functions for daytime transformations, such as change the time zone, extract the time information. We can also have blocks for doing basically math operations, computing logarithmic. We have data type transformations and nested data transformations, some conditional operations such as combining rows into columns, as well as blocks for aggregation, computing aggregations. In the case of having strings in our data sets, we can have very basic string transformations, some more complex functions such as joining to dataset or replace some numbers in the columns. And lastly, we have also functions related to time series, such as resampling time series data, etc. The user can, as I showed before, can just press the add button or use the search box in order to identify and use the intended block. In this case, for this example, I'm just going to use the simple renaming of columns. So again, by configuring the parameters, so basically writing down which columns we want to rename. In this case, it will be the battery capacity, and just write a new name that we want. And saving it, we see that the pipeline starts to take form. Next, we have the input blocks. This is for undertaking iterations or loops. I'm just gonna show here that I just use one just for the example. User has to provide the configuration parameters for this one. First interesting part is the machine learning blocks, which can be used for training a model and then applying it. As you can see here, the engine supports various models, also supporting the scikit-learn library. These are basically for applying a model, and also further down we have for evaluating a given task. As you can see here, we can evaluate undertaking classification task, a clustering or regression task, where the user again can select the evaluation metrics that he wants to use. And then further down we have the various algorithms that can be used for training. I will just add an outlier detection that can be applied. Again, as you can see, the user has to configure the parameters, so which previous blocks you want to apply this. In this case, select the models, the existing models that he wants to apply. In this case, it's an elliptic envelope algorithm. And continue it with actually implementing this into his pipeline. Here, as you can see, it was quick, sorry, you can get error notifications down at the bottom if something is not wrong, so the user can recheck his configuration. And moving forward, and the last step is the output blocks, where basically the user can decide where he wants to store his results. It can be exported to a CSV, JSON or Parquet file. You can write the dataset to a Mongo database or even store the results to the cloud. And then also store the CSV file or the JSON file. Again, he can configure here, he has to configure the parameters. Set, let's say, the name of the results and the description. This is what we saw, is the graph view. We have two other views, the table view, which we will see now in the results view. The table view for each of the blocks used in our analytics pipeline. The user, by clicking on it, he can see a sample that is obtained through dry execution. See basically the columns and the data that are included there. And going in the results view is basically where, using the output block, we can design how our results would look like. You can choose between various graph types like area, bar, donut, or heat maps. And then on the right hand side, you can see that you can provide the configuration such as the title for the axes, etc. And also here, sorry, I'll just go a bit back. We have this configure button here, where basically clicking on it, the user can define the type of samples they want to use during a test run. If it's going to be a fixed sample size or a sample percentage, define what percentage of the data they want to use as a sample, and define also the position from which the sample data should be taken in the case of non-optimized datasets, as well as if they want to run this pipeline in batches, if this is compatible with the pipeline. We also have what we call the scheduler, so he can schedule for the execution of his pipeline, so put a start date and an end date, the frequency, how often it shall be executed, and the exact schedule details. The engine also provides information if it's the analytics pipeline is valid, so if it doesn't have any configuration errors, and if not, he can basically finalize and execute the pipeline itself. Now I will move on by showing one of the examples already made by our data scientist. This problem, as I mentioned at the beginning, is an unsupervised outlier detection for detecting point anomalies on the battery capacity of this given satellite. And the objective is to train and apply an elliptic envelope to detect point anomalies, i.e. power spikes in the satellite's batteries. So starting with the data input blocks, we have the, let's say, installation of the use of this satellite telemetry data. followed by some data preparation blocks, such as renaming columns, aggregating over the specific ground stations, and renaming of the columns. And then what is basically done is we use an analytic envelope to train our model and then apply it to detect anomalies. These again are followed by some so here basically is the application of the outlier detection. Before that, we have the training with analytic envelope, and then we have some further data preparation steps in order to create a new column in order to have like visualization of the results. This is basically what this new column called anomaly visual does. Followed by some basically basic math operations. And then finally we store the results to the cloud. So if we go now so this is basically the results. So if we go to the results view, basically, and select this given block, we can see how the results will look like, a sample of the results. And here is where the user, as I said before, can configure the parameters for this graph. And by running this pipeline, we will see that basically the actual results, how this would look like, and the prediction of the anomalies. So this is what is shown here. So we can see basically that the anomalies shown with dark green follow the same pattern as the actual battery capacity. In this case, this is the evaluation we can give for this type of check. Now moving forward, another function of before I go to a second example, another function of the Misbehaviour engine is where we can retrieve the results and create retrieval queries. In the case in REWIRE, we send this to the risk assessment module. So here basically we provide a title and a description of the retrieval query and how it will be retrieved, in this case through an API. And then we move on by selecting the assets, the fields basically, that we want to expose through this API. You can either select them all or just the specific ones. In this case, I will be selecting them all. On the right-hand side, you can see you can define query parameters to be used to filter the search query results. In this case, we will be using the observed date time, and this will be like provide a range in order to filter the results. And moving forward, we can see that we can test these search results and run a query by setting the required dates. We can see the sample that is acquired, as you can see here. Forward, the user can get instructions on how to authenticate himself, or instruction of pagination, and the endpoints where the engine supports both the get and the post method. Now I will move on to our second example. Sorry. So in this case, it will be a classification task, as I mentioned previously, identifying South Atlantic anomalies, where the objective is to train and apply an XGB booster on latitude and longitude information, telemetry data, to predict research due to these anomalies. This is basically the pipeline created by our data scientist. As you can see, again, we start with reading the data set, and due to the highly imbalanced data set, a first draw of random sample from the normal events was made, shown on this branch, and these rows were then appended to the main branch in order to create the full data set. Again, you can see the various steps undertaken, starting with the data input, data preparation blocks, and then down here we have for the model training, we used a support vector classifier. This was initially used to train with default parameters to predict anomaly due to the South Atlantic pass, using only latitude and longitude. In addition, another model was trained with an XGBoost classifier using the same feature, and then again applied to the full dataset. Moving forward, we have this basically, if you remember before, one of the main blocks we can use is for evaluations of our task. So basically going into the table view, let's fast forward here, and using the classification task block, we can see the evaluation of this task. Basically here we can see an accuracy for this task of 0.96 almost has been achieved, meaning that the engine correctly classified approximately 96% of the data points in the evaluation set, indicating a high overall correctness of the model prediction. An F1 score of 0.96 again, which is very high, signifying again that the engine is effectively finding most of the actual anomalies, while also having a low rate of incorrectly flagging normal instances as anomalies. A precision of 96.6%, indicating again that the engine flagged the data point as an anomaly, and it was correct 96.6% of the time, so suggesting a low rate of false positive. And finally, a calculated recall of 0.96, signifying that our engine has successfully identified approximately 96.6% of the actual anomalies present in the evaluation dataset. So altogether, through these metrics, we can say that the model has correctly identified the area where the satellite is passing as a potential cause of misbehavior, and providing thus evidence that providing evidence for the engine effectiveness in this task. So this is my part of the presentation. So I don't know if you have any questions for the overall presentation now.
Thank you very much, Spiros. I appreciate it for the enlightening presentation. So let's proceed with the closing. So I would like to thank you all for today's presence. I would like to notify you that the next webinar organized by REWIRE and Trust will take place on Monday, the 12th of May, at 12 o'clock set. It's going to be an extended set of webinars for day, which is provided with online, and we are going to have the opportunity to talk about the IoT interoperability for security, advanced crypto, and advancements in manifestation mechanisms. So thank you very much for today's participation. We look forward to seeing you also on Monday. So I think we can close this webinar. I would like to wish you all a nice weekend. Thank you very much for being here. Thank you very much, Spiros, and I would like also to thank our colleagues and partners from both Hotels and Charemis, and also the coordination team of ENTRUST for first of all being present and help us for organizing this series of webinars. All the material will be uploaded to the website and YouTube as well. So thank you all very much, and look forward to seeing you in the next two webinars as scheduled. I would like to wish you all a nice weekend.